Hello, welcome to Oceanology International 2020. Greetings to you in your time zones and nations and homes, wherever you may be joining us. We're pleased to bring you this virtual session. This particular session is on ICT for uncrewed systems and operations. And it's an exciting lineup we have for you. We have three speakers. Vegard Haugen from Kongsberg is going to speak to some of the communications technologies making these things happen. Paul Ferve from Satellite Ocean Applications Catapult is going to also speak to communications and operations concepts. And lastly, Mike Gunderson, who is from Marine Advanced Robotics, will talk to us about the autonomy side of the question. So the flow here, we'll have these three speakers, and then we will engage in a questions and answer session here amongst the panel. This is an exciting topic. It is an emerging technology area that is inherently cross-cutting. And so we're very pleased to have these three excellent speakers and organizations with us. So with that, I am going to hand this over to Vegard, who is our first speaker. And the floor is yours, sir, or the screen is yours.
Thank you. Okay, thank you for that. My name is Vegard. I will talk to you about improved efficiency in unmanned operation. And I will focus on one of the products we have developed and are putting out in the market to achieve this. So short, my topics here is a little bit about the technology, because you need to understand that to see what we're having. I want to talk a little bit about the challenges in communication in a maritime environment. And then we're gonna round it up with some different applications where actually MBR has been the solution to achieve that operation. My background is from the Navy. I sailed for 19 years, so I've been in a lot of operations, and mostly of the time, this was what we have, and I guess a lot of you guys have seen this. So we ran our operations with VHF, and then we had the digital cameras or video cameras that we could actually get over with a crew or a patrol boat or something, and they come back and we could actually look at it. But that was what we got around with, and it worked. We did get our mission done. Looking at it now, this is where we are and what we actually want to do. A full digital network where everybody is on the same page, so to say. So common operational picture. And how have we done this? What have we put into on the technology to achieve this possibility? And I will come back to what we've done here. In this scenario. So maritime communication, so requirements, what should it be? How should it look like? But in the end, of course, minimum loss of data. It should absolutely work in a maritime environment. What about security, latency, topology, and operational wise? How is it to install? How is it to use? Looking at the challenges, we have several ones, and I would say main one is the flat sea fading. You want the signal to go from A to B, but due to this flat sea fading, you have reflections from the sea. And just to say, flat sea is not a calm day in the summer. It's up to 2 meters wave height, and you still got this kind of like interference where you actually can lose signal or block signal or lose some part of the signal, which interrupt your communication. You also have this near-far topology where you maybe have a vessel over the horizon and you have one close to you. And how do you do this dynamic? You need to talk to somebody far off and somebody really close. In addition, we are at sea. So you're rolling, pitching, turning, and all this comes into play. And again, and one of the last year, what about if a vessel goes in between, or you have an obstruction in between, or you're doing a critical operation. How do you cope with that? And here are some of the answers when you're using the MBR and how we do it. We have the antenna gain, and we have a real-time steerable beam within the radio. It got a high dynamic range and adaptive power, meaning it can cope with this near, far, and also rolling and pitching. And we have a high link margin. To look quickly into the radio, this is the MBR, and it's a beam-forming antenna system, so phased array. And with phased array, mean that we can get a narrow beam like a parabolic antenna, only purely digital. So inside this antenna, it's 60 antenna elements. This board is only 30 by 30 centimeter, and it's all controlled by 17 FPGAs, which together and combine make us electronically steer the beam in any direction at a great speed to get all those assets together. If you look at this in a practical matter, on the left-hand side is traditional antenna, which we all have seen, 360 degrees, great in that way. However, it's limited in range, definitely limited in bandwidth, and it's also easy to monitor and jam if you're looking at this gray part of it. While the MBR do have a narrow beam, constantly changing and adapting to movements, range, roll, pitch, and so on. This is, again, electronically steered, so you don't have to do anything. This is fully automatically done in the antenna, which gives us greater range, more robustness, higher link margin, and also higher throughput. The range we have is divided in two. So on the top here, it is the MBR. They are based upon civilian standards and regulation, and that's the approval. We have this larger set of antennas. We have two of them. One MBR 189, that is directional. MBR 179, which is omnidirectional, meaning it can beam form in 360 degrees. And then we have a range of MBR 144s in different variation depending on your application or assets you want to put it on. They're all equal when it comes to software and functionality. The difference is that these antennas only got 4, while, as I said, there are 60 antenna elements within these. So that only limits the range. You won't get the same range out of these ones as you do out of the larger one. We also have a military range. The military range is called CRE, and it's the standards that are different. You will find the same name in these as well, so they kind of like add up. Quick look at facts and numbers. It is a beyond line of sight system, purely IP based. So meaning this is everything. You got to feed it with power, and out of it, there is the Ethernet cable coming with a traditional RJ45 connector. It's got a 16.5 megabit payload, so throughput. It is point-to-point and point-to-multipoint. And not at least, it got deterministic latency, meaning that you have full control of the latency in the radio, the bandwidth you allocate to each of your assets, knowing that every time they got their slot, they are able to send and receive. So there is no fighting over bandwidth like a traditional Wi-Fi, which in a lot of operation is really crucial. Looking at some user cases where MBR has been a key factor. And I can start with what's really hot nowadays and what everybody's talking about, and that's this autonomy, remotely operated platforms in a lot of different variation, application, and purposes. I've just gathered 4 of what we have been doing. This is sounder USV we actually make. Got a payload dock in here where you can change to any systems you have. So meaning multi-beams, single beams, high PAP, and so on. Remotely operated or autonomous. Here we have a kind of like a squadron of multiple vessels where they're working to protect an asset, fully autonomous. In between, they're sharing data, and one of them is checking everybody. This is the X Prize challenge. Same here, radios, a lot of different communication, having a Hugin on board, running autonomy, doing survey. And again, mine hunting, MMCM operation. To show you one of the things we did here last year, we pulled the first fully autonomous pipeline inspection. And again, this was for Equinor, large oil company in Norway. They wanted to see if they can conduct inspections of their pipelines going out in the North Sea by sitting in their office in Bergen. So we gathered the Hugin, which is Kongsberg's UV. Unfortunately, we were not allowed to use the sounder as a USV, so sending a unmanned vessel, that was due to safety. So we had to play USV with Simrad Echo. We had an MBR here, acoustic communication with the Hugin, and from the MBR to shore in Bergen. And then from there on, VPN down to Equinor, which was sitting in their office. So this is the coverage of the radio. Bear in mind, it was 650 meters up. So we have about 120 kilometers out. But they sent out the Hugin and the USV going out to a platform, 94 kilometers, going back again, and it did this double up. So 360 kilometers fully autonomy by the guys sitting in their office looking at this, which was great. They were impressed, and it was a successful demonstration that you can actually launch these kind of autonomous vehicles and remotely control it. Another great example is when you're looking at remote areas where you have little, less, or nothing of comms. This is from Svalbard, far up, where the university in Trondheim had a test of, they call it the Pope. So they set down this buoy through the ice and have a lot of different sensors that was going to monitor a year through, just drifting with the ice. So in here, they had an MBR comms. They also have Iridium. And the idea was that when the Coast Guard vessel was up there, aircraft was flying over, if they had drone out, they could fly over, connect ad hoc, upload the data, and go back again. I mentioned briefly MMCM operations. When you're looking at MMCM, of course, that's then you're talking mines, and you don't want people in there. And traditional mine hunting or mine clearance has meant going in by the vessel. They are moving away from this. So instead of having this mine vessel going in, doing the search, they are sending in USVs, UUVs, they're using UAV to get distance. So these go in, check it, and everything is being monitored real time back to the operating vessel. Yet another example of combining a lot of different assets, the full picture back. Sorry, it's a lot of gray in here, but still the idea is that if you have a lot of different assets, you want to share that with somebody in control or your operation room. The whole idea is to have a robust system that can deliver this. So again, here is just a screenshot from the operation room onshore, showing the sensors of their rib, their mother vessel, and what they are doing in real time, so they can task them in different way if needed. I also said I was going to end up showing this digital picture of how we are doing things now. This is a scenario we did also last year. And here we have different assets. We have several vessels, we have boarding team, aircraft, drone, different cameras, and operation room. So on the aircraft, we have a radio, we have a payload with different sensors, and they have an operator station inside. Of course, high altitude, extreme long range, checking out what is going down and can stream this down to the vessel. The vessels also have their own radio connected to their systems. Some of the vessels have drone with a radio on board to share with their vessel in one-man's operation or daily operations, but also to share with the group if something larger is going on. As I said, we have a helmet camera for the boarding team, so the operator is able to see what's going on in real time, instead of seeing that traditional VHF, which we had before and still have, don't get me wrong. And again, different cameras and sensor uptake depending on which vessel it is. And all of this is then transmitted into one big operation room where they can sit and choose. Do they want to see the aircraft? Do they want to see the drone? Do they want to see the inspectors? Do they want to control the cameras on the vessel? And of course, the software in the background is running different layers that everybody see in real time what's going on. Chatting, uploading, you have your own MBR cloud in it, so your own cloud in the network. So all in all, a great achievement if you're looking back at that digital camera and that VHF I started off with. I'm going to run a quick video of this scenario, and we take it from there. Sorry you guys can't hear the sound here. However, it's not any important info coming out. But as I said, in this scenario, we had a fishing vessel that was suspicions for the Coast Guard in Norway. They get tasked to go and check it out. The operation room is monitoring. The aircraft is up in the air, sending live stream down. And then as the vessel, Coast Guard vessel approach, they send out their drone, they send out their inspection team, and everybody is taken back to the operation center on board. Yeah, it's not a black and white camera. This is just for the effect. So that's how it is. And here you can also see the different range we have of radios adapted to different assets. So this is how the Coast Guard, together with other governmental department in Norway, are running now, which is great. Just going to show you a little bit about demonstrator ranges. Vessel to vessel, we see up to 70 kilometers, and from vessel or ground to aircraft or UAV, it's more than 200 kilometers. So just to sum up a conclusion, it is a robust, safe, and reliable communication, secure network in the way that you own your network. It's your local. It's not going through or via anything. Again, then there's no limitation in data usage, and of course no fee. It's your radio, so you use it how you like. And again, with these radios, I would say your operation will improve and will be more efficient. Yeah, last but not least, my favorite slide. If you only focus on a problem, you might miss the easy solution. So with that, I would just say thank you and hope it was useful. And if you have any questions, take that in again.
Thank you. And for those of you in the audience, contact information can be provided. There'll be a facilitation of Q&A, as this is a virtual session. And of course, we're talking amongst ourselves and we can't hear or see all of you, but we hope you enjoyed that presentation. So next up, Paul will come talk to us, continuing the discussion of network systems, although in this case, we'll hear some more about satellites in the picture. So Paul, again, the screen is yours.
Thank you, Justin, and thank you for that fascinating introductory presentation as well, Vegard. So one of the things I'm going to touch on today is how do we move from the actual aspects of operating in a theatre to looking on a global basis. Bit of background about myself. Paul Fever, I work in satellite communications, and when I first started working on these systems back in the 1980s, I was working on a first digital system over satellites, which was Inmarsat-C while I was at British Telecom Research Labs. I then moved to Inmarsat, and we had the opportunity to move from the very high performance telex systems that we were putting in place then to IP over the satellites. Just more recently, I'm working in an organization called the Satellite Applications Catapult. It's a non-profit research and technology organization in the UK that really looks at how do we bring the use of satellites to everyone and also steer the future. So I'm going to talk a little bit today about satellites in a maritime context. So you can see a bit of background there. And I think one of the things to note, of course, is that the maritime environment is a fascinating but also very dangerous place. And the expectation is as we exploit more of the value of the resources and our oceans more effectively in the future in a sustainable way, that the only way we can do that by keeping people safe is to exploit autonomous systems. And I'll come back to some of the applications a little bit later. But actually what we're seeing is even in the space sector now, we're having more and more autonomy just to get the economies of scale. So here's an example of the Starlink reusable launch vehicles that SpaceX used to launch their satellites. And of course, this is on an ocean barge, autonomous ocean barge. You wouldn't want to be sitting on this barge if something went wrong with the launcher as it comes back onto land. So we're starting to become very attuned to the possibilities of autonomous systems. I just want to say a little bit about satellites. In fact, Vegard was just mentioning the fact that he had Iridium on some of his the systems that are deployed to provide that over the horizon global coverage. And the reason Iridium is interesting is because it has a polar orbit and basically then therefore gives coverage over the poles, but it is designed as a voice system, has the aspect of inter-satellite links that allows reach across the entire planet. Something to be cognizant of is when we look at geostationary satellites. So here's an example of Inmarsat's, one of Inmarsat's constellations, Inmarsat 4, and it's the distance that the electromagnetic waves have to travel to get to the satellite. So these are 36,000 kilometers above the horizon. You can see here from a range perspective to the base station or to the ground station, it's 38,000 kilometers. So to go up and back is 75,000 kilometers normally, and to go twice to get back there again is 150,000 kilometers. And that, when you take into account that light travels at 300,000 kilometers per second, means it is about half a second to do 2 hops. And that has been a real challenge from the perspective of controlling remote assets. Even though you can get significant capacity on geostationary systems, it doesn't really help very much when you're trying to put a human in the loop in remote robotics and control. You need autonomy, and you can do directivity or directing the applications. But we're reaching a point where perhaps we need to do more. So this is where some of the evolution of the systems is really interesting. It's not just maritime and space. Aviation systems are increasingly autonomous. We're seeing the impact of drones on airspace management. How do we make that safe? We're seeing connected autonomous vehicles being a real drive for the next generation of systems that we will all use in the road networks. And the reason that is interesting and important, and the drive is to reduce road traffic accidents and essentially fatalities and serious injuries. There are a significant number of injuries per year. It's the biggest killer, for young people in society today. Just to give some context, something like 1,700 road deaths a year in the UK. It's not acceptable. Anyway, so the systems are getting to be put in place to make safety. Just touching on the reason this colourful chart at the top, it shows the spectrum bands. And I just want to, these are the ones that are used by satellite systems. At the bottom end here, we have the L-band and S-band systems that Inmarsat-C operated in and Iridium operates in. Above this, we have C-bands. That's typically used for VSAT communications and quite often to things like cruise vessels or to oil rigs. Then we have the military spec X-band. The other ones that are highlighted here, this block here is the KU band is used for satellite TV, satellite broadcast, and for communications. And at the higher frequency bands, we will call this KA band, it's used for the very much the broadband systems. And you can see why. The bandwidth is much higher, you can get more through. And from a user perspective, it doesn't really matter as long as it gives you the service you need. Just touching a little bit on the first generation low Earth orbit satellite communications, I mentioned Iridium here and Globalstar, both designed to provide handheld communications. There's a maritime variant here of Iridium called OpenPort to provide, it bonds 3 channels together. All the electronics inside just give you the steering capability. The Globalstar, if you look at that, the reason it's not full coverage is it doesn't have inter-satellite links, so where you need to be in reach of a gateway. Some of the investments now that are taking place, for instance, in high throughput satellites to provide coverage. So here's an example, Viasat providing very high performance, high throughput satellites, covering, for instance, here the Great Circle routes as best they can from GEO for aviation. But I think there's some really fascinating developments that are taking place now. And I'm going to touch on non-geostationary orbits. And I'm going to give 2 examples. The company that I used to work for and develop systems for, Inmarsat, has historically been a geostationary satellite operator. So you can see here is a fleet of Inmarsat satellites. In fact, the 1 generation, which is the GX Ka-band wideband system. What you can see Inmarsat is investing in now to come into service in 2022 are elliptical orbit satellites, specifically to provide Arctic coverage. And these will provide the high bandwidth services that really have been lacking with regard to supporting activity in the Arctic region. Unfortunately, they don't cover the Antarctic because the satellites are traveling extremely fast when they pass the Antarctic. And it's only here at about 40,000 kilometers of altitude that they really stay around long enough to deliver an effective services. But the interesting thing here is both for aviation and for maritime, it brings high bandwidth capacity, but the latency challenge still exists. Let's look at one system that is providing a lower latency. It's in what's called a medium Earth orbit. And the first generation of medium Earth orbit satellites used for high bandwidth communications was called O3b, which is now owned by SES. And SES, that shows you the satellites, these are the satellites, they've got multiple steerable beams that can be directed as the satellites go around the Earth. Now, all satellites in all orbits go around the Earth, and if you're in geostationary, it takes 24 hours, so it appears to be stationary. Because these are at a lower altitude of about 8,000 kilometers, the implication is that the orbits precess. So in order to cover one particular location, you need to steer the beams from the satellites, since you get these kind of structures. The other challenge is that because they're lower, they don't reach up to the sort of 78 degrees north that the geostationary satellites can. And you can see here, it reaches to about 50 degrees latitude, or thereabouts, 51-ish. So just clipping the southern part of the UK. But now, SES are investing in their new mPOWER range, which extends these MEO satellites to include inclined orbits to cover both the Arctic and the Antarctic region. And again, the business models for this are associated with cruise ships and exploration and resource extraction, very much commercial services. So again, very interesting, lower latency, but not the lowest. I'm going to touch on 2 systems which now are being deployed, which are large constellations, sometimes called mega constellations. And I'll touch on 2 of them. The biggest by far at the moment in terms of advancing the density is Starlink, which I touched on with the autonomous booster configuration, you can see the satellites ready to go into the launch vehicle. Already we have hundreds of satellites in orbit, with, by the time it's fully deployed, it'll be 1,500 satellites. Now you can see that they're not in really in polar configuration. There's a few in polar orbits or highly inclined orbits. Others are inclined orbits to provide services where there's maximum density of users. So they could be useful and interesting for some applications for maritime, especially in this kind of oceanic regions. They do have inter-satellite links to connect these satellites that are at 500 kilometers. They're even lower than Iridium satellites. But you can see the ambition with regard to providing massive increase in capacity. These are for mass market applications. I'm going to finish with one of the satellite constellations actually that the UK has invested in quite recently, which is OneWeb. And this, as you can see, is a satellite constellation which is in polar orbit, and they're at 1,200 kilometers altitude, so still relatively low. So typically a two-way latency, including all of the waveforms and the gateway functions, is less than 50 milliseconds. That's round trip. And that starts to become possible then to use it for autonomous system control or direction, but even for robotics. Just a couple more slides here. This is just the first generation of OneWeb, and you can see that the satellites have multiple beams and they move very fast with respect to the users on the ground, and the terminals handle all that complexity. In fact, they use antennas very much similar to the ones that Vegard was talking about, with digital beamformers to track the satellites. You don't have to worry about it as a user. They're solid state potentially in every application in the future, certainly for the land applications. The maritime ones, maybe they'll have a combination of different techniques. But the interesting thing here is the gateway reach. Because the satellites are at 1,200 kilometers, a bit like Vegard was saying, you can use for an aviation platform, you get an extended range. So with a number of gateways, these are the actual gateway locations, and there will be more in the future. You can reach just about every part of the globe with low latency, single hop connections. So I just wanted to bring that to your attention because it does change the art of the possible for the future, where we've got both low latency and high capacity systems that can be deployed. And this really, it won't necessarily be for everything, but it might enable, for instance, those in-theater operations that Vegard was describing before to operate in just about any planet part of the globe. And really what this does is it brings in essentially the potential for the future to realize the value and really fully exploit unmanned systems. And they might actually be sitting out in territories where perhaps they're there just in case. So for instance, around an offshore renewable energy farm, to keep people safe, you may have autonomous rescue vessels that are just deployed when they're needed and give very rapid response. So we might see a whole future where not only are we seeing that the platforms that move vessels autonomously, but actually we're seeing the systems, the whole system become autonomous. And that's all for me. And perhaps I'll talk a little bit more about the other aspects of positioning and situation awareness when we get to Q&A.
Thank you, Paul. Certainly a lot more interesting things to think about. I learned a lot more about orbits than I ever had before. Much appreciated. We're going to round out our formal presentations with remarks from Mark, who's going to talk to us more about some of the specific vehicle activities going on the sea surface. So Mark, the screen is yours.
Great, thank you. Let me get this set up. All right, thank you, Justin. And thank you to Jamie and the entire Oceanology team for inviting me to participate in this great panel. And I'd like to start by wishing the virtual audience, depending on your location, a good morning, good afternoon, or good evening. Today, I'm going to talk about how we use autonomy as a force multiplier. But before I do that, I'd like to introduce you to our company. Marine Advanced Robotics is a maritime robotics company based in the San Francisco Bay Area. Our patented technology is called WAM-V, which stands for Wave Adaptive Modular Vessel. You can find our robots in 10 countries around the world in various applications for our military, commercial, and scientific customers. Our patented technology has several advantages. The stability of the platform results in better high sea state performance across multiple applications. The modular design allows the vessel to be quickly taken apart and reconfigured or repaired. WAM-Vs are designed to be easily transported, whether this means by trailer or in a container or on the deck of a ship. The scalable design allows us to build WAM-Vs in sizes ranging from 2.5 meters in length to over 40 meters. The biggest one we've built to date was a 30-meter variant in length, 30 meters in length, and had approximately 5,000 nautical miles range. The stabilized central platform is perfect for deploying any sensor where stability matters. Sonars, cameras, uncrewed air, surface, and subsurface vehicles are just a few examples. Last, but certainly not least, the WAM-V design is extremely energy efficient. So to answer the question of why we need a force multiplier in the first place, I want to take a look at a specific project we worked on. It was a hydrographic survey in the Great Lakes, which you'll see in the box here. If we zoom in a bit, you can see all the Great Lakes, and you can see in the box there the project area that we worked on. As we get a little bit closer, we can start seeing the planned survey lines. And if we zoom in a little bit further, represented in that box on the bottom right there, you can actually start to see the individual survey lines. Obviously, a lot of survey lines, a lot of line miles go into a project of this size. So our force multiplier approach pairs WAM-Vs with crewed survey vessels. The WAM-Vs autonomously track and trail the crewed survey vessel, and the multiplier effects depends, of course, on how many WAM-Vs you add. As you can imagine, the swath width can get very wide, so the number of WAM-Vs you bring onto a project will depend on the size of the project. If you have a very large project, you can bring in a lot of WAM-Vs to really reduce the number of days it takes to get the project done. Our force multiplier approach allows us to operate with direct line of sight communications, and we use a mesh network which provides excellent reliability and high throughput for sonar data to transfer the sonar data back, and to also have multiple sensor feeds for better situational awareness over the entire project area. Our control system allows us to quickly adjust WAM-V offsets in real time, and it also gives us the ability to respond quickly if there are any problems during the operation. This is really beneficial if you're talking about operating in high traffic areas or in near very shallow waters. So the success of what we call the Mega Swath project was never a given. This group of forward-thinking companies, eTrack, Sandpoint Hydrographic, QPS, R2 Sonic, and our company, of course, Marine Advanced Robotics, came together to accomplish several industry firsts on a NOAA survey that was part of eTrack's contracted work. Nevertheless, at the end of the day, we still need to produce a high-quality survey that met the requirements of the contract. Additional requirements included ASVs that matched the capabilities of the survey vessel. Productivity, of course, is key on these big projects, and you don't want to put out ASVs that are significantly slower or can't handle the same sea state as the crewed vessel. We also needed autonomy behaviors that augmented the crewed survey vessel. It was important to us that we didn't increase the size of the crew when we added the WAM-Vs. We don't want to bring on WAM-Vs and then add on an entire crew of people to operate them. We also needed a versatile software for integrating data because our approach requires that the operator sees all the sonar data on the same instance of the acquisition software so they can ensure that you're getting proper coverage in real time. We needed intelligent survey sensors that didn't require a lot of input from the hydrographer because they'd be managing multiple sonars at once. And we needed an integrator that could pull this all off. We got all of that and more with this group of companies. So here's a little bit about here's a Mega Swath overview. Kind of see see a dashboard display and you get a sense of what the hydrographer is looking at while in control of the Mega Swath. For this project, a boat captain piloted the crewed lead vessel. The picture on the bottom right is from the crewed vessel, and in the top left image, the crewed vessel is represented by the white monohull boat icon. The hydrographer was on board the crewed vessel and controlled all 4 sonars, a dual head on the crewed survey vessel, and 1 sonar on each WAM-V. You can see that sonar output in the image on the bottom left. The WAM-Vs autonomously followed the crewed survey vessel at the required offsets to achieve the desired overlap in the sonar coverage. There are 4 images across the top row, and you can best see the overlap in the image second from the left on the top row. The top right image gives you an idea of what the bottom looks like. In order to give you an idea of the importance of bringing all the sonar data together on one screen, try to imagine if the sonar data from each sonar was on a separate screen. There'd be no way you can ensure that you're getting the required overlap until you combine all the data, which typically doesn't happen until the end of the day or potentially even later. So you wouldn't have any idea what your overlap was until then and whether you had any holidays that you had to fill in. The middle image on the bottom row is the view from the WAM-V. So there were a couple of firsts on this project. It was the first time to our knowledge that a force multiplier approach with 2 ASVs in formation with a crewed survey vessel were used on a NOAA hydrographic survey project, and the first time ever where sonar data from more than one sonar, in this case 4 sonars, were displayed on one instance of the acquisition software. This is a necessity for this type of force multiplier approach because you need, again, to see all that coverage from all the sonars in real time, and then you can make any adjustments you need. As the bottom depth changes, as you go around obstacles, you need to be able to adjust things in real time. Here's a little look from the trailing WAM-V as the WAM-Vs autonomously follow the lead vessel to the survey location. Now, having controlled multiple WAM-Vs myself on a project, it's really nice when you can just set them to follow and then go about your business on some other tasks as you're transiting out to the survey location. And in this video, you're actually going to see a look at the entire Mega Swath project, so you kind of get a sense of what we did in this project. So as you can imagine, we learned a lot from our first Mega Swath project, and we have continued to develop the force multiplier approach for multiple applications. For large-scale hydrographic survey projects, we've gone to a slightly larger WAM-V, a 22-foot variant with multi-day endurance so we can support 24-hour operations. Going into this whole project, our goal was to add the WAM-Vs without an increase in crew size, and we accomplished that goal. We also learned that there were a few things we could do with the autonomous behaviors to minimize the burden on the hydrographer. We've also automated the swath overlap to maximize the efficiency. And the next step for us is to build more WAM-Vs for this role. We'd like to put 5 WAM-Vs on the next Mega Swath project. So I started this with the question of why this force multiplier approach. And then of course I zoomed into this location in Lake Huron to give you some perspective on the scale of what we're talking about. I hope I've done a decent job explaining how we implemented the force multiplier approach on a hydrographic survey project and the advantages to that approach. But now I'd like to zoom back out from this spot in Lake Huron to get a view again of the Great Lakes. Just again, to kind of give you a sense of the scale of what we're talking about. And now let's, oh, excuse me. Restart that real quick. Jumped ahead a little too fast. Anyway, let's again zoom back out. So from our project area in Lake Huron to again a view of the Great Lakes. And then we're going to zoom back out to our original view. To again, talk about the scale. And then let's jump over to the Pacific Ocean. So we obviously have a lot of ocean to survey to bring mapping of the ocean floor up to modern day standards. we believe that this force multiplier approach is the most cost-effective way to achieve that goal. Thank you all very much.
Thank you, Mark. And thank you to all of you. Those were some excellent presentations. And if this were a classic in-person session, we would find ourselves with a great deal of time for audience Q&A. So thank you for being concise and so well-spoken and prompt. Obviously, we don't have an audience, but for those of you who are viewing this, whether it's through the official Oceanology sort of Q&A function, we'll attempt to, in not real time, but with a high latency, to steal a term here, we'll try to be responsive. And certainly, as you saw slides go by, there was some contact information. So I'm sure everyone here on the panel is happy to be contacted directly or indirectly. So as we enter some Q&A here, and we'll spend some time discussing a few things. You know, the one topic I'm certainly interested in broadly here, and I'd like to invite everyone to comment about, we presented a lot of potential, whether it's the potential for force multipliers, whether it's the potential for large networks or remote operations of pipeline inspections. There's a lot of exciting ideas that have been brought up here. And we've mostly been speaking or presenting as technologists, the folks who bring the technology to bear. There is, of course, the end user question, the human beings, whether they are operators or accountants and lawyers in the mix of all the things we've talked about. So I'd like to open a discussion about assurance of autonomy, assurance of communications, and the question of trust. And it's a broad question, sort of deliberately, but I'm going to invite all of the speakers to provide some comments about how they're addressing that subject, or if they're not addressing it, how they're experiencing it as an impact on the operations here. And I'd like to just sort of go in speaker order. So I'm going to go back onto mute here and invite Vigard and then Paul and then Mark to offer some remarks on that topic.
Yeah, thank you. And it's definitely an interesting question. As some of you might know, this is something Kongsberg is really working on, both in, you see the technology to actually achieving it, but also in conjunction with regulatories and class and so on. Because one thing is to get that boat sailing autonomy. But of course, you have some regulations at sea, which the navigator is kind of like doing, and it's his job and what he's trained to do. But suddenly you have a boat out there, and well, you can maybe monitor with a camera, but you need to make sure that it's actually doing what it's supposed to do in an environment with a lot of other vessels. So, so we have been working actually several years now to look into how can we adapt regulation and regulatories and technology to actually achieving to sail autonomous. And I think still it's way up there if you're looking at bigger vessels, to platforms and so on. But that's a small step. But as I see it now with the technology, it's more, well, in the beginning, it would at least be an aid to the navigator, a helpful extra helmsman and officer of the watch and a couple of extra eyes, but it's all digital. So I think that's where we going and what we're doing now. So definitely interesting to see how far we can take it and where will it end? When will we actually be able to fully sail autonomous around doing what, well, as a navigator we did and still doing.
Thank you. Paul, thoughts?
Yes, I think this isn't unique to the maritime environment, and wherever we're seeing autonomous systems being deployed, and they're typically deployed for either efficiency or safety reasons, safety in terms of taking people away from a hazard, or doing things that the human operator is perhaps finds difficult to do, this is actually not, so it's not a single environment where we have these challenges. So I'll just give a couple of examples. In the road transport sector and the road network, we're seeing a significant drive towards autonomy, but it's actually a staged approach. You have levels of autonomy. In fact, the first level are considered to be driver aids. They're essentially advanced driver assistance, so ADAS type models. So you would have a adaptive cruise control or automatic braking system. So the cruise control, if you like, is a kind of an autopilot. And historically, if you can stick it on autopilot, go make yourself a cup of tea, that's a good way to have an accident. But having the aspect of at least being able for the machine initially to detect hazards and try and respond in anticipation of the user perhaps not being in control. Now, this sort of technique also is applied already in the aviation and maritime sectors. So you would have an autopilot, basically put your autopilot on, off you go. Actually, it'd be a really good idea to have that coupled into your sonar system or whatever to make sure that you don't go over the top of a reef, for instance, or if you're in the aviation world, have a collision avoidance system so that you can detect another entity within your airspace that is likely to be causing a hazard to you. So there are systems in place, and in the maritime environment and the aviation environment, those are fairly well developed for the type of operation that we have today. So in aviation, we have something called ADS-B, automatic dependent surveillance beacons, and they are essentially, there's different techniques, but they allow an aircraft to describe its trajectory to other airspace platforms with a similar capability, an ADS-B receiver, and to alert the pilot, or even in some circumstances to take autonomous correction. And in the maritime sector, we have, and we're all familiar with it, the AIS systems, automatic independent surveillance systems. And again, these are designed to allow for, as aids to navigators, when you're operating in perhaps an observability denied condition, fog or rain, or, so if visibility is denied, how can you be sure that when you're steaming along at 10, 15, 20 knots, that you aren't actually steaming straight into another hazard, a non-mappable hazard, something that happens to be traveling in the same environment as you are. So these techniques of adding in capability and intelligence to systems to provide improvement safety are already happening. I think what it becomes interesting is when you take the human away completely, or remove the need for the human to actually be in control of the vessel or the airframe or the vehicle, it does bring another level of consideration with regard to assurance. I think what we will see is that, for instance, it's likely that the road network leads because of the drive towards, as I said, the number of road deaths. And we're already seeing this with the likes of most vehicle manufacturers now have very advanced driver aids, and some of them completely autonomous. Tesla is a case in point. And you only have to look through the data to realize that they're already safer than the human driver statistically. And that's in a relatively constrained environment, but one which with lots of hazards. You need to follow the road network, you need to follow the rules of the road, and you need to operate in a mixed environment where you don't know whether the other platform is autonomous or not. You may need to indicate intent. So we are seeing, for instance, not only optical indicators on a vehicle, but potentially vehicle-to-vehicle communications. So that is now been a technology that's been around for about 10 years, but it's increasingly the case that it's being made safety critical. So the standards under which the systems are tested now are much more stringent than perhaps non-critical systems or typical wireless systems have been operated in the past. And that's really indicative of the level of diligence that's being put in place to make the underpinning systems as good as possible. When we're operating in a wireless, in a maritime and aviation environment, those short-range techniques don't necessarily work so well. You need more anticipation. You need to deal with the difficulty of uncertainty in this space. There could be subsea hazards as well as surface hazards. There could be, weather hazards. And actually, what it does is it emphasizes the need to provide information with high integrity to the decision-making entity, whether it's a human or a machine. So my view on that is that we will see some domains accelerate the adoption of this technique, and then they will be technologies that can be transferred into the different sectors. And I think the maritime sector will be a beneficiary, perhaps, of some of those mass market developments.
Certainly. Yeah, great inputs there. Mark, on your side of the fence and of the ocean, what are your thoughts on this general topic of building assurance in your end user base and their trust in operations?
Yeah, so I mean, what I would add is kind of, you need to do that incrementally, right? The trust with the end user and with the public at large, I think comes in incrementally by people using the systems, by people seeing the systems out there operationally. And certainly for the end user, right, they need to know that the systems work reliably, that they do what they expect them to do. They understand how to address problems as they come up. And so I feel like that's really an incremental approach that really kind of builds as you use the systems and as people become more aware of the systems and understand their uses and their limitations and kind of how we are continuing to progress the technology going forward.
Thank you. Yeah, important perspective. So I'm going to put out a question that is, it's sort of a little beyond the scope of what we've talked about in this panel, but I think it's incumbent upon us to address. So most of our discussion here has revolved around essentially above the water's surface, right? From satellites to radios to uncrewed surface vehicles and vessels. You know, we saw some photos that showed undersea systems. This is not a session on undersea telemetry explicitly, but I'm just curious if you all might share some perspectives you've come across, whatever that may be, where your subject that you've shared with us here intersects with the water surface and then with the complexities of telemetry and operations below, right? So just as a reminder for the audience, the minute we go underwater, a lot of the tools and techniques we've talked about here essentially start to fail us. So this is a case where you're welcome to just sort of call pass. If you don't have a relevant comment to offer, that's entirely fair. But I'm just curious as we go through again, and we'll do the same order, just any thoughts about how your topic connects with the subsea environment and maybe some either challenges or opportunities you see on that side of the air-sea interface, as it were. So you're first, Vigard.
Yeah, thank you for that one. No, well, the experience we have with this, of course, we make UUVs and we do acoustic and we try to make good communication below the surface as well as up and actually satellite as well. But in my experience, that the way it is now, it's you get bits and pieces and fragments that you can kind of like tick off. Okay, it got pulse, and you can tick off. Yeah, it did get to the waypoint, and that's like the limitations as it is now. And of course, you want to increase that to get more information up. And another aspect is that, like the MMCM I was talking about. Okay, man out of the loop. You want to have the information, and again, it's a UUV going under there. It's a USV following. It's a communication either by satellite or by MBR or other comms means that transport this back. And we see when the UUV pops up, because eventually it does either run out of battery or it got high classified information that you need to take action on. Okay, let's say find a mine, and it pops up, and even though if you have standard communication there, it's like really low on the surface. So you even struggle when it is popped up and surfaced. And so I would say that communication part for below is really hard, even though it's in the surface, or when it's going down, it's hard to extract something from a great range, given it's not like a huge UAV which can carry whatnot of different equipment and satellite and so on. So yeah, it's a hard one if you ask me.
Thanks. Paul, any thoughts?
Well, yes, it's an interesting topic area. I mean, the challenge is that the seawater doesn't actually allow propagation of electromagnetic waves very well. In fact, it really doesn't allow it at all. It's just that sometimes if you've got very low frequency waves, they essentially tunnel. So for communication with submarines, you use very long wavelengths that kind of like a little bit of the wavelength goes under the water, and then you can communicate. But that means very, very low capacity systems. You just simply have only a few bits per second through the system. So it's not really very suitable. So I think what we will see is an increase in the combination of different technologies. Will have surface-based systems that are managing the assets under the subsurface assets, that we'll see a combination of acoustic and tethered type mechanisms for doing that, and that there will be networks of acoustic systems underwater. I think what really is fascinating though is what do you do with the data and how do you bring it back together to life? And so one of the things I'd like to think about, some of these challenges that we face in other domains as well. You've got IoT systems and sensors that might be deployed on animals or on infrastructure, and then you've got the kind of wide area sensing techniques, and they're very different types of data. And how do you bring that together and use techniques such as artificial intelligence or machine learning that can operate at different scales than the human brain is used to dealing with? So you can extend the kind of concepts of computer vision to be on a different scale, in terms of dimension or in terms of time. But I think one of the things that's really fascinating is the potential for using gaming technologies, augmented reality, as a means for bringing that data together and to assist in the interpretation so that it becomes much more meaningful to the operator, and bringing the long time baseline and the immediate aspects together. So I think that's a fascinating area for development. That's probably as much as I can really add.
Thank you, Paul. Mark, I imagine you've got some specific ideas for your platform at the ARC interface.
Yeah, I mean, that's pretty much all I'd add onto what Paul and Peter were talking about, is just this, because of the difficulties and the challenges they've addressed, our platform has been used to launch ROVs. We're getting ready to do AUVs, with the whole idea there of bridging that gap, becoming a multi-domain surface platform, right? And we launched the underwater vehicles, we've launched the aerial vehicles and then acting as essentially a comms node for multiple assets. So kind of going forward, I mean, that's also part of the role we see ourselves playing to address some of these challenges.
Yes, certainly, I think, and of course, from an oceanology perspective, again, if we were here in person, this is when I'd say things like, go down on the trade show floor and look at all the exciting booths with all the diversity of technology that would come together into systems of systems to address these questions. Hopefully you'll be able to do a little bit of that digitally. Sort of two more questions. We'll probably round this out. The first one I'd like to sort of, again, the option to pass exists, but it is 2020. We are here virtually. We are not here in person. The world has inherently been different these past 6 or 8 months. And I'm just curious if you have any specific anecdotes from the technology area you're working on, or even maybe not from that area, but from your business experience. How has the global circumstances of reduced travel and changed way of operations impacted what you've been telling us about today? And again, if you don't have a great example, that's fair. But if you have one, I think our audience would be very interested in understanding what's going on in the COVID era for you and your piece of the industry. So just quick remarks, if you have them, are welcome. And again, we'll start with Vigard.
Yeah, hey. Well, again, that's it's interesting, and I think that in one way, COVID has kind of like accelerated it, because suddenly you are in a position where, whoa, I really should have invested, or this is something I really should have. Okay, I need less people in the loop, but still need the same data or even more data to kind of like minimize the time I'm operating and the efficiency in that operation. So we see actually an increase in what we are doing and providing to this. And bear in mind, we make all the different sensors, from the bridge to the situational awareness to the comms to vessels. So we see like the picture of what is going on out there. But definitely, I see a trend that people are getting to it, and I think it in some way have accelerated this development and this drive.
Thanks, Paul.
I completely concur. 100%. I mean, basically what we're seeing now is that there's an increased recognition of the need to be digitally connected to be effective in terms of delivering business. So we're able to do this presentation now, even though we're in completely different parts of the world. If you don't have good connectivity, you can't be part of the community. And if you are restrained in terms of your ability to go out and get data, you want to be able to pull it back all the time and have that understanding of what's happening in the environments you're trying to manage and support people's safe operations. So this is really creating a drive towards communication systems, towards positioning and navigation systems that are going to assist with making our future more autonomous. It doesn't matter whether it's in the farming sector or in the mining sector or in the transport sector, you know, everywhere there's a demand and increased recognition that you need to be connected all the time to be part of that community, the global community, and drive economic wealth. And that's where I think we're seeing the sort of conjunction of terrestrial and satellite and other systems as well, local area network technologies with wide area network technologies, and it being completely seamless to the user. You don't actually care whether your device is connected on your local network or on your wide network, and in the future on your satellite network. You just need it to work. And I think that's going to be increasingly the case when we have autonomous systems and dependency on machines.
Thanks. Mark?
Yeah, so I absolutely agree. And I think the thing I would add, I mean, we've seen an acceleration in terms of, you know, what our customers are concerned about and how they can use unmanned assets to do some of the work they're doing. I give an example of a customer, you know, a lot of the survey projects, you know, required quarantines before they started a project, right? So, you know, you start building that into your project, you start shortening time, you know, and certainly in some of the areas where you're surveying because your survey window is short. And so you're really trying to do more in the time that you have. And so a lot of them are looking at unmanned technologies to be able to help them do that.
Great. Yeah, thank you. You know, and my quick comment I'll offer is that I've been impressed by the sort of adaptability of our community. We've used that word a few times, right? The oceanology community may be one, right? And you know, we've had our hopes of reviving in person. We've adapted, we've evolved. There've been webinars. Personally, as someone who the trade show scene and the conference circuit was a huge part of my life, I just find it fascinating. 8 months later, I sort of still feel in touch with you all, and I feel like this is actually working. So I thank all of you for that. I have sort of one final question I would throw out. I think we're sort of creeping up on a reasonable length of time here. And this one is sort of the inverse of the last one. So with a little luck in 2022, we will be coming together again in some form, or if we're not together, our avatars and our virtual technology will perhaps be substantially better. But what might you bring to the audience to, you know, we're talking about ICT for uncrewed systems and operations, you know, fast forward a year and a half, 2 years, any sort of modest predictions? I realize predictions are always risky and make people uncomfortable, but what do you think you might be telling us about in a few years at this sort of same venue? And we'll go in the same order here. So if Igor has had the bad luck of having to think fast, and Mark has had the bad luck of sort of not having as many choices to say, but we'll just stick with that for this final round.
Great, thank you. No, I will say in 2022, I think I can provide you with a couple of autonomous runs with ferries and container vessels that's actually operating autonomous between, their routes. So I believe that in 2022, you guys should be able to see our first run with that. I don't think it will be without any people on board for the safety, but they will for sure do everything fully autonomous.
Very exciting. Well, we look forward to that.
Yeah, me too.
Paul?
Oh, well, it's a very interesting year, 2022, because if you remember on my slides, I showed several systems that are being built right now. So we will have the Arctic coverage high performance satellites of Global Express will be able to pull bulk data back from those systems, and we'll have Antarctic and Arctic coverage from the SES-03B or the mPOWER systems. And we'll have 2 mega constellations, which will actually have been proven technology now, providing low latency communications for operational systems. So in a sense, our job is done then. It's now up to the rest of the community to go and use this stuff, right? I'm kidding, of course. So, but I think it's very exciting times because it does provide the basic fabric under which we'll be able to do so much more for the next 5, 10, 20 years. And it starts now.
Great, thanks. Mark, what are you going to bring to the table?
Yeah, so when we all come together again in 2022, we'll be able to present on kind of the next evolution of this force multiplier approach to hydrographic surveys. So, you know, the multi-day endurance, the scaled up vessel, the greater number of vessels on it, and just this better use of autonomy across the board to again minimize the burden on the hydrographer, because we want to still keep it as one hydrographer, right? So that hydrographer could now be operating 5 to 10 sonars and 5 to 10 unmanned assets, right? So how do we do that in a way that, you know, that person can handle that during their shift versus trying, you know, pulling their hair out because they're trying to manage all these different things. And, you know, obviously at certain times things aren't going to work properly and they have to be able to troubleshoot that, address it, and keep everything going. So that's what I hope to show in 2022.
Great. Well, this has been an excellent session. I certainly really appreciate all of your time to participate in this unusual fashion. We've covered a lot of ground. And again, to the audience, we'll just sort of say thank you for your attention wherever, whenever you're viewing this session. And with that, we'll say farewell from Oceanology 2020 ICT for Uncrewed Systems and Operations. Thank you.
Thanks, Justin. Great.
Thank you.
Bye-bye.
Thank you.
Keep safe, everyone.